Yeah, we're excited for this collaboration between FIU DSC and University of Ottawa DSC. And yeah, so let's get started. Next. So the topics that we're going to be going over today a bit, roughly, is we're going to get into linear regression. What are some of the applications of it? Gradient descent, which is my personal favorite. I love gradient descent. Bias and variance, and then we're going to hand it off to Ahmad to code. And yeah, we'll see. If anything confuses you, do not be worried. We will cover it. And yeah, so next. So linear regression. And this is really the basics of this is a very statistical thing, but it's important to learn nevertheless. And on the graph on the left, this is what we usually see in everyday life when we're looking at graphs. We see this continuous graph that goes up and down and then fluctuates. And when we're talking about linear regression, we're really looking at that one line in the middle, the dotted light blue line. And really, when we're dealing with regression, we're looking at the graph on the right, because we're not going to have most of the time a full functioning graph. We use linear regression on discrete points as the one on the right. And so you have points of data, and these are values. It could be about anything. I'll tell you some applications in a bit. And then we plot this line in the middle. Now, what is this line? Why do we even have it there? And this is referred to as the line of best fit. It's the line that best fits the points that we have. And what that shows, sometimes it shows us what kind of relationship the points have, and based on the axes. And when we're looking at the axis, which is the horizontal one, this is often independent variables. So it's variables that you're given in the first place, depend on anything. Well, that's why they're independent. And then the y-axis, which is the vertical one, we look, and these are the ones that are going to give us these different values. So then this line of linear regression is often used to predict. It's often used to extrapolate data based on how many points you have. And we'll show you some comparisons. But in high school, I don't know if you guys remembered, but y equal mx plus b, the equation of the labels on the left, yeah, it's back, and it finally has a use. You know, obviously it's always had a use, but we've wondered why use it. Java says, well, you're gonna use it somewhere. Boom, application. And now we're gonna go into a bit more. Looks a bit more difficult, but it's the exact same thing. On the graph on the right, if you look at the equation, y equals not theta and zero with a subset of 1 times x. So we're looking the 0 sub 1, our slope. It's how we vary our linear regression line. And you'll see that a lot if you go into linear. They use Greek letters like theta to symbolize, but like I said, nothing to be scared of. And then you see the lines that from the points down to the dotted line. We'll explain what that's for later, but they're very useful. And in fact, it's all about those lines. Next. So why linear regression? Let's go into some applications. So when we look at stock analysis, much more complex than this, obviously. I don't recommend that you go and analyze stocks just based on linear regression, but it gives a good of curve that we can easily see between these high fluctuating peaks, and we can see what kind of relationships there are in our stock analysis. And then with other applications, for my Canadian people, You guys over in Canada, you have an effects monitoring program, and they use linear regression, in fact, and they use it for fish wildlife. They use it on trouts, and linear regression you can use on wildlife to estimate the weight or future based on the time of the year. So you can find a lot of relationships with it. So it's useful in that. And then a bit more applicable application, predicting house prices from square footage. And while it may seem intuitive at first, you might think, well, the more square footage, the more expensive it's going to be. And while only true, it's always good to have a quantitative measure to have the exact line so that you can predict points that you don't already have, values that you don't already have. And yeah, so that's one thing. So next, please. And so then we look at the real use of linear regression, because the graph that I mentioned earlier simplified. There's maybe 10 points, 12 points, and there you can kind of see what the line looks like. But when you're looking at linear big data, that's when it starts to become a lot more useful. And you have these points, and these are a lot of points. You can kind of see where the line would be if we hadn't done the calculations on it. But this is a much more useful application. And here we're looking at a graph that uses linear regression that compares on the X, it compares the money spent on marketing on TV versus on the Y, the sales you have on that certain product. And while the numbers are not really bold and specified, it doesn't matter for this application because we just want to know the concepts. And so we can see, even though, keep in mind, linear regression normally just gives a correlation. It shows us more or less a relationship, not this is a fact. And this is more useful for things that are more ambiguous. But here we can see that with linear regression, it's a positive relationship. And as more on marketing on TV, you have greater sales, and that's logical. And then we look at those gray lines that I mentioned earlier, so useful, yet you would never think of them. And these are the lines that from a point to our linear regression line, these will give us how we calculate how close our linear regression line is. Excuse me. As we have more data points, our line will move and calculate, and we'll show you exactly that in the next slide. But these are, the gray lines are one of the ways that we can quantify that. So I'll pass it on to my good friend, John. Who has to be unmuted.
Okay, sorry about that. So cost functions, what are they and why should we care about them? So Hermes was talking about something called like our actual points compared to our regression line. We call this a residual. Residuals give us an idea or an estimate of like how correct our model's prediction is. Now, just a disclaimer, I'm going to be using linear regression. It falls under the classification of a model. In machine learning, this is just general terminology. So these residuals are put into something called a cost function, which tells us the accuracy of our prediction. Common cost functions includes functions such as the mean squared error and absolute error, which basically gives us kind of the distance between, or the measure of correctness between the predicted value and its residual. We can see this clearly through the example that this graph is giving and Hermes talked about before, such that we have our predictions And we have our regression line that we're fitting those data to, and we're just trying to generalize it as best as we can. And this cost function just kind of like describes like the errors. So now that we talked about a little bit about cost functions, let's talk about how we can optimize it. How can we make these cost functions better? So in general machine learning, there's this very popular optimization technique called gradient descent. What gradient descent does is optimizes this cost function such that it is minimized. So we are given some hypothesis function. The hypothesis function basically kind of is the function that we're predicting, which will give us our predictions. And then we have our parameters, theta 0 and theta 1, which in the example Hermes gave can be sales in the TV variable. And then we have our cost function. In this case, it's just the mean squared error. And our goal is to minimize this such that the errors are as low as possible. So how do we minimize this? What is the gradient descent algorithm? So in gradient descent, we minimize by taking something called the gradient of the cost function. As you can see in this visual, kind of like just to visualize it, we can take partial derivatives with respect to each variable that will point towards the steepest slope or the steepest area such that it's minimized. Now, a very important point to note is that this is predicated on the initial predictions. So it's minimized based off of like where the initial prediction is. So it's minimized towards some local minimum. It's not guaranteed that we're going to find the global minima that the cost function can minimize towards. So yeah, and then we can see the algorithm if you want to like look at the pseudocode. We have an assignment for each variable and just take its partial derivative with respect to the error function. Now you may be looking at this alpha, like what is this alpha? This alpha is just a learning rate, which specifies the step size. How much do we want to learn at each iteration in which we're optimizing our regression line. It is also important to know that we take these partial derivatives synchronously. What I mean by this is before we assign new values, we have to take the partial derivative because you can see that the error function is dependent on the other variables. So we kind of need like that it to stay where it's at first, and then we make the updates after we compute the gradient. Now this is gradient descent. You don't have to really worry about the calculus too much. Just know that it's a method such that we can minimize the error function. So now we know about gradient descent. Let's go into regression with multiple variables, more than just one or two. So yeah, this is like very big brain stuff. You guys may be a little bit intimidated by this, but don't worry, the concepts stays the same. So we see that we can fit a regression line in almost any dimension. Now, the highest dimension we can visualize is 3 dimensions, and we can fit a hyperplane that serves as like our predictions for like a 3-dimensional type regression or predictions that we want to make. So in this case, we have miles per gallon, weight, and then horsepower. And then we can fit like with these 3 variables, a hyperplane or some sort of regression plane in this case, in order to give us like the prediction based off these 3 associated values. Now, there's also, you can see like how the hypothesis function can change with expanding increased variables. And we can also see like the data set. This data set I grabbed it from a Brazilian data set that's from some Sao Paulo beer company. We can see that we have the medium temperature, the max temperature of a beer, and the consumption of that particular beer in liters. Sorry for not translating it. I was just kind of went over my head. But yeah, so this is just simple stuff. Like you don't really have to, it's easy to visualize this in either 1, 2, or 3 dimensions, but we can do this for any dimensions really. Like you don't really necessarily need a visualization. We just need to know like how it works at a finer level, because in code, like it's a lot of these things are kind of abstracted this way. So now we can move on to the intricacies, or what are some problems we may face. The problems are bias and variance. Oh my goodness. So bias and variance. If you can click the next transition, bias. It's everywhere. You're going to see this a lot in machine learning. People always talk about it. So bias, what is it? Bias are the assumptions made to simplify the model. We generalize the bias, and we need to be careful with how much bias our regression line or model has, because this can, as you can see, like cause to some underfitting. We can see this bias graph is underfitted. It's not really generalizing this correctly. This is more so like it kind of plateaus after a while, and like if we're using this line as a decision like metric, we're just going to get like increasing linear predictions. Then we have something called variance. What is this? Variance is it describes the sensitivity of the model such that the smallest changes updates the regression line very, very minutely, and it focuses more on the nuances in the data. So why is this bad? Well, this is called generally overfitting. This is bad because, yeah, we may like be very accurate on the small data that we're training in, but throw new data into there, and then it's just going to do horrible. Like data hasn't seen before. It's just going to say, but like, yeah, it's not going to fit very well. So the variance is actually a huge problem if it's too high. Same with bias. So how do we combat this? Like, how do we like find the sweet spot with variance and bias? I'll discuss this in the next slide. So a way we can synthesize bias and variance to like give us really satisfiable results and predictions is techniques such as regularization. Regularization is a technique that combats aforementioned overfitting and underfitting problems and regression tasks by adding an additional penalty to the cost function. What is this penalty, you may ask? The penalty is actually the weights or the coefficients of the model that we are trying to optimize for. So like with each coefficient, we want to shrink it towards zero. We regularize this such that it's kind of like even. So like, yes, we want our model to fit the data perfectly, but we also don't want it to fit too perfectly. We want to like optimize it towards some zero, so such that it's not fitted exactly like how we want it, how like the sub or the training data is. And when used strategically, we can find satisfiable generalizations even on data we haven't seen before. So this is a very, very, very important topic for regression tasks such as linear regression, and even more complex ones such as logistic regression and regression tasks in general for like more of the complicated machine learning models. So now with that, I'm going to pass it on to Ahmed to go through the code tutorials and visualizations so you guys can see how this works in implementation.
Thank you for passing the baton along. You guys are just gonna have to bear with me for a moment while I switch over to the Colab. Okay, so we are coding this Colab in Python, and I am using the software called Google Colab. I'm actually gonna post this here because it is read-only, and you guys can choose to play around with it. But basically, it's a web service that allows you to host your code online and share it with other people. Actually, sorry, this would be a better, I probably shouldn't do that. And we'll post that in the chat shortly, but basically we are going to cover the code of linear regression, and we're going to show you some visualizations on how it's done. So as we covered before, linear regression is just a model that fits your scatter plot the best you can. And sorry, guys. Okay, cool. So you take your line and you try to fit your scatter plot the best you can, like we said earlier. Now that said, we have two variables. There's the prediction, which is represented by U. And then there is the, then there is the actual ground truth, which is represented by Y. So Y in this case would be your actual measurement, which is in blue. And then you have your red line, which is your U, and that's your prediction. Now, with that in mind, if you guys take a look here, I am importing some libraries. And what that means is it's just an external piece of code that somebody else wrote that allows me to use it and abstract information that I would otherwise have to write myself. So over here, you create a figure and you create axes, and you're able to create this plot here. Now, what's interesting about Python is that this Python library is it's able to adjust automatically to whatever values you insert. So you don't really have to worry about setting anything up specifically. So I just generate a random data set here, and I split it into different subsets. So there's 50 samples in total, as you can see here, and they would be these points right here. And yeah, I'm sorry, give me a second. I'm kind of blanking out, like I don't know what to add here. Sorry, I'm just checking the chat. So next up, I should go back and rehash the knowledge that this line is called a hypothesis. And what your hypothesis does is that it is an estimation of what your value should be based on what you've already learned. So given these blue dots, you make a line of best fit, and it is able to give you a best guess. An example of this would be, for example, a linear model that's trying to predict the price of a house, where you have X as the surface area of the house, you have Y as the actual price of the house, and U is the predicted cost of the house. So given over 100 different homes, which are represented by X, Y pairs, where once again, X is the surface area and Y is the actual price of the house, we use this model to try to predict what the cost of the house will be. And I actually have a model over here. Now, sorry. Whoops. Sorry. So, sorry, I forgot to adjust for these values. However, take this example. We have these points, and you have a line that goes down like this, and that's your residual, right? And sorry, and then U is the actual value that's represented by your line. What happens is that because you have, I'm sorry, jitters. This is my first time presenting, guys. You're gonna have to give me a second. Sorry. Anyways, so going back to it, we have U, which is our prediction, right? And that's a line that's represented here. And you have your Y, which is represented by the dots on your graph. And your residual is represented by these lines. And the goal is that we want to minimize this residual. We want to minimize the total amount of error that we have. And that error is given by our error function, which is once again represented by mean squared error over here. Now, I will go over the I don't want to bore you guys too much with this code because, so I'm just going to go over with the visuals. So you'll notice this is a data set of how many hours you study and how much you get as a percentage. And you'll notice that obviously different students get different results. Your results may vary depending on how much you know and how much you've prepared beforehand. But more or less, it shows that the more you study, generally, the higher you'll get on a test. And so we're going back to gradient descent. I just wanted to cover this really quick to like really hammer it in, but we take the partial derivative as seen below, and we try to move towards the minimum, which is the minimum's like the lowest mean squared error that we can possibly find. Now, with linear regression, luckily for us, it's very simple, and usually the global maximum is very easy to find. However, as we go into higher level functions, sometimes we may not be able to find the best solution, and we may end up in wrong valleys. And this is the beast that I wanted to get into. Sorry, I just wanted to change one thing. And I'll just show you the result. Given a data set, given a data set, you would graph a line of best fit. And what happens is you start with given values where theta 0 is 218, and then your theta 1 is 2,500. And if you start it from the beginning where it only learns once, like where it initially tries, you'll notice that the line is completely in the wrong direction. But over iterations, it slowly gets better at guessing. So if I go back to, for example, 20 iterations, it's not that great of a fit because it's only tried 20 times. And so the line is only getting slowly better step by step. But when you are able to move it along to 2000, for example, it has much more iterations to be able to learn and update its values. And that's why learning rate is so important, because it specifies how fast you move. And if you set your learning rate too high, you would usually end up missing your target and not being able to reach that minimum. I'm just gonna ask the chat, do you guys want to go over the class that we have for linear regression so you guys can kind of get an in-depth view on linear regression and how it works in code, or would you rather see more of the visuals? Okay. Okay. So above here, we have the libraries, and we have matplotlib, which is the library that we use to actually draw the diagrams that you see here. Then we have, sorry, this is just the styling for matplotlib. We have scikit-learn, which is an amazing tool if you want to learn machine learning or at least experiment with machine learning as a beginner. And we have dataset generation. Now, how many of you guys are familiar with classes? Like, are people familiar with classes all that much? Okay. Just for those that do not know, just to put it shortly, a class is just a blueprint for a program that you want to write. Say you need 10 programs running at once, or 10 pieces of code running at once. You would use a class to make a blueprint, and then you can make 10 of that. That's really abstracting it away, but I just don't want to go into the semantics of classes. At the end, we could post links for people to learn Python if you guys want to, if you need to read up more about classes. To begin, we have our constructor over here, and we have our learning rate set to this. We have the number of iterations. We have theta 0 and theta 1, which these two over here. We have and we just set training features to none for now. And it's just a constructor, nothing fancy. Then we have our training function. And what we do is that we create a shallow or a deep copy rather of the array for just, it sometimes causes errors not to create a copy. And then we loop over the, we loop over the iterations. Like we go, for example, if we pass 300 or 500, we would go 300 and 500 times. And this is the actual sum value 0 and sum value 1 is the sum that we were talking about here in batch updating of gradient descent. And then this is our theta 0 gradient, and we take that sum value from before and we multiply it in the same way that we did before. So theta 0 gradient is the full gradient that we have here, or updated value, rather. And then here, sorry, I skipped a lot, my bad. And then after we create our gradient function, we update our theta values to the theta gradient. And we print out our values for what our updated theta values are every 200 iterations or so. And that's what we call epochs, which is how many steps you've taken or how many times you've run over your data set to learn from it. So you'll notice that over time, over epochs, the actual values for theta 0 and theta 1 change over time, and pretty quickly too. Like it quickly jumps into the thousands after only 200 iterations. Now, one thing to note is that, for example, if I set learning rate really low, right, it's gonna stay where it is. Whereas if I just remove a few zeros, you can automatically see or instantly see that it learns a lot faster and is able to adjust. And that's what you need to be careful about, because once you go too far, yeah, it doesn't even process. It just goes beyond and keeps bouncing off and goes to a number that's way too high for my current Python runtime to handle. Do we have any questions so far, by the way? Just about the code or implementation or the mathematics? Like just about the code specifically, like I know you guys are asking great questions in the chat. Like I've been keeping an eye like in the corner, but like, NumPy is like it's a library that lets you deal with matrices, and matrices are, I don't like, are you familiar with the, oh wait. Okay, so yeah, not a lot of people know what matrices are. Sorry. So I'll quickly go over what a matrix is, and this is just to explain what NumPy does. But NumPy is just a numerical library, but one of its strong points, especially in the context of machine learning, is that a lot of data gets represented in tables, also known as matrices. And so, for example, whoop, I keep forgetting. You have A equals to, and you have 1, 2, 3. I'm really doing my best here. And so you have these values and they're stored in a 2x3 holder. And so this could be any type of information. It could be like a table where you have, I don't know, age, weight, height, and then you have a row for person number 1, row for person number 2. And so matrices are just a tabular way of storing information. And NumPy allows you to work with those really easily in a way that's much, much faster than regular Python could. Does that make sense to everybody? Are there any questions about NumPy? Okay, sorry. So afterwards, after we have our training, sorry, I went off on a tangent about NumPy, and I was telling you guys about how it changes the learning rate and how it trains. Then there is the plot line, and this is where matplotlib really shines. Matplotlib is a library, like I said before, that allows you to plot these sorts of graphs. And so through matplotlib, I'm able to make a linear space, which just represents a variable. And then I'm able to create the hypothesis, which is this line, and then plot it. And that's what I call here after I have trained it. So just to recap, the steps are to go through to create your data set first, to normalize your values, to create or apply a simple regression onto it with your class, and create your data set and then train on that data set. Plot your points, plot your line. You'll show your difference, and you'll be able to see this graph. Now this just gives you an implementation, and there are other resources that we can show you on how to learn Python and how to implement machine learning in Python and other languages if you guys choose.
Well, actually, Ahmad, would you like to? You have the gradient descent visualization. Could you maybe show like where? I know they're just visualizations, but where you could maybe start to add 3D space, because you have linear space and then possible.
Sorry, I didn't hear the last part. You kind of cut out for a second.
Oh, well, I was just saying. So we're talking linear space, and so you mentioned linear space. Is it possible in PyPlot maybe to do 3D space? And if so, further, maybe somebody's interested.
I don't actually have an implementation with on me on higher dimensional space. Unfortunately, I tried to run it in Google Colab and it crashed on me horribly.
But it's possible, right?
It's yes. It's just not like you can't do very complicated figures with Colab. It ends up like burning through your resources.
Cool. Okay, sorry.
Yeah, I can show some other examples of linear regression. There are examples online that I can show. There are higher dimensional examples that I have, but nothing on this document. Although I do have resources on multiple linear regression implementation as well.
Well, actually, maybe we can go back to the slide, go to the final notes, and then see if people want to see the implementations and some further stuff, maybe.
Sorry, which final slide do you like? The final,
No, just
one?
the implementation, like the supervised learning, unsupervised, so on and so forth. So please go ahead.
Oh, okay. Like this slide, you mean?
Yeah.
So, anything in particular?
Oh, me? Yeah, it's John.
Yeah, I'll do this one. So what we briefly talked about was a form of supervised learning. We talked about linear regression. Now I made kind of like I insinuated that there's multiple types of regression because it is true. There is. Now there's logistic regression. There's regression in general. We can see this like with more complicated machine learning algorithms or techniques such as gradient boosted machines, as well as for random forest type of classifiers. There's also a subset called unsupervised learning. Unsupervised learning is basically how can we identify label that we haven't, or data that we haven't seen before. We don't know what they represent, but we kind of like want to extrapolate them and kind of like make sense of them or identify them. An example of this would be like, okay, so we have a bunch of data that we've like ran through like some sort of like testing. Let's say we're testing like a rocket and like we're observing some unknown chemical compound like variables, like with like the rocket's booster. We don't know what this is, but we can cluster them in order to like kind of like make sense and like kind of like give us like a more general or a more idea of like what this data actually represents. This is unsupervised learning because these are unlabeled, unstructured data that we make sense for ourselves, that we have the computer learn to make sense. we're not programming this explicitly, we're programming it implicitly by having an AI agent make these distinctions for us. Now we have like some of the cooler applications within reinforcement learning, which is where you see like AlphaGo and like these chess agents beating the world's best humans in like these games. Or we see self-driving cars trained in simulations, and like we take these models and plop them onto like an actual hardware car, and we see that it performs just as well because we trained it based off of like iterations. It's learning from its mistakes, and we're from all these like examples, like tested values that it's simulated, it learns like the optimal like decisions to make from the mistakes it made during training time or simulation time. Now, if we can go to the next slide, we can kind of like wrap this up. I hope you guys learned a lot about machine learning. We kind of like wanted to give you guys more depth instead of breadth, but there's definitely, we encourage you guys to explore more concepts of machine learning. I'll give it off to Hermes to wrap this up and explain like some of the like the minor ending details.
Awesome. Yeah, thank you, John, for that explanation. Now that is the cooler stuff in ML. I know that this math can seem kind of mind-boggling, but it's important because that's, you know, that's how we get those cooler applications like self-driving cars and so on and so forth. So first of all, I'd like to thank you guys all on behalf of all of us for coming here. Great teaching to you guys here at DSC at FIU. So we're the Google Student Developer Club at FIU. And if you haven't signed up, you are missing out. You should. And you should join our Discord, which you can just scan it and join like that. That makes it easier. Or use the there's also our Instagram. There we post a lot of our next events and a lot of important stuff going on in FIU DSC. And as you see our picture, well, this was pre-COVID. It's a lot more empty now, but it's starting to repopulate. And it's our beautiful campus at Medici, it's MMC. Sorry, it's like a long word. And we're based in Miami. And so we'd love, whether you're Ottawa, sorry, like you can probably join our Discord, but for our events, it's kind of difficult because it, you know. But please follow our FIU. We'd love, if you have something to get in touch with us, we have in our future slide, we have our contact. So next, oh, the invite is invalid, strange. John, if you could send a code in the chat, maybe. And I could explain this for you, Ottawa, but I think that Ahmad, you can take this over, and I'll take over the next slide, if you'd like.
Sure. So we're the University of Ottawa, and with me is our team lead, Skyla. So this is obviously what our campus looks like, and this is Taparejo, and obviously pre-COVID. And we also have a Discord as well that you guys can feel free to join. This is, whoops, sorry, I was trying to zoom in. This is our QR code, should you need to. We also still have the readable version of the slideshow. So if you don't scan or find these links, feel free to scroll back up in the chat and just copy that link now so that you have it for safekeeping. It's view only, so just can't edit it.
Okay, great. So yeah, that's you, Ottawa. I also recommend that Discord. And next, please. So then this is us, you know, us are the three musketeers, Ahmad, John, and myself. You can find our LinkedIn. I know Ahmad prefers Discord if you want to reach out to him. We're indifferent, but definitely if you want to add us on LinkedIn, feel free to do so. I love to people. I got my love for machine learning from a workshop taught by my mentor Adrian, and I hope that we can kind of spark that into you, or if you already had it, you make it even more. And yeah, so if you have any questions, now is the time. Anything, if not, if you remember afterwards, just contact us. We'll be free. More than glad to help.
We'll stick around for a few minutes if you guys have any questions, but we do thank you for coming here, and we really do hope you found this informative. I know it's Sunday, I know it's 7 p.m., and I know this was probably an overload of information, but should you need it, the slides are up. You can contact us for information or like resources to find out what you want and what you would like to know.
Also, I'd like to say people that are at FIU, we have, I forgot to mention, but it's really exciting. We have what's called dev communities. And these are specifications in certain fields. We have one for ML/AI, one for web dev, mobile dev. And we have one for competitive programming, and we're trying to see how those go, and really meant to foster. So like if you're interested in AI and ML, they're meant to foster that love very specifically. And questions about that, DSC in general, our workshop, anything, who we are. Okay, we have one from Azar. So I guess John's muted, so I'll take this one over. Oh, okay.
Sorry, I'm going to stop muting myself because I can't unmute. So machine learning is actually like more of like the umbrella term for like everything that like learns like implicitly. Deep learning is a subset within machine learning, and these are the techniques that kind of like simulate like how we think like neurologically. So that's why we see like a lot of neural networks coming into play for like object recognition, text recognition, kind of like deep fake generations also because of deep learning. So it's like more so like programming it based off like how scientists observe or simplify like how our brain works. Obviously, I'm saying simplified because like we still don't know how our brain works, but it's like their best like interpretation of like that. Hermes, do you have anything to add?
Yeah, sure. So John, you explained it wonderfully, but also it's very, very simple. Machine learning, as we've talked today. And when you're talking about learning, you're talking about, well, neural nets we didn't cover in this one. We actually do have a workshop that John and I taught with our other colleague. And if you contact us about it, we can send you a link about neural networks. And deep learning is about these neural networks, lots and lots of parameters. So it's very complex. And we're talking about big data, a lot of data and to consider. So yeah. Any more question?
Yeah, some of the cooler
also for our model.
GT3. I think that's really cool. Like there's like really cool applications coming out of deep learning. It's for example, deep learning, because of deep learning, stuff like object recognition, computer vision's considered a solved problem now, because now we have like comparable results. So like how we see ourselves, a computer can see just as well if it's trained correctly.
Just to add something, there is one other issue, which is that they don't learn as quickly as humans. So like they can perform much better, but we haven't reached a point where we can like you need almost up to 100, like hundreds of images to teach a model like one specific item, right? And so we haven't gotten to a point where a computer can like look at it once and almost perfectly identify it every time.
Yeah, it is true. And that's one of the setbacks that we have for machine learning, but the benefits just completely outweigh that. It is costly also to run some models and train, because it gets to a point where you're dealing with thousands and thousands of images or pixels. And but the good thing is when we see, for example, and this is an application that's very modern and happening right now, and people are getting exposed to it, is with companies that are starting to do self-driving cars. We see that sometimes the reaction times much quicker than humans would at reacting a child passing in front, to reacting to a potential hazard. That's why machine learning is becoming more and more relevant, but there's also plenty and plenty of applications. So I really recommend it. Yeah, if there's any more questions, if there's nothing, then we could probably wrap up the workshop. Yeah, thank you for coming, and thank you all of you guys. This is already a big step into learning ML, is going out looking for workshops. Like I said, that's how that started, and yeah. Awesome, thank you, Azar.
Any general questions you guys may have? Like, some people think like AI is becoming it's encroaching on like ethical issues. This is a very, very, very interesting topic to look into if you guys are looking about reading into this. Is AI going to take over the world? It's already taken over the world. It's adopted. It's not the future, it's the present. But AI is not going to kill.
There actually, I mean, this one's off topic, but there actually is a TED Talk about like how encroached, how much it's encroached on like our daily lives without us even knowing it.
Yep. Yeah, it is. Like,
we can actually, we're gonna post this on our YouTube channel. Once it uploads, it does take about an hour to be ready for us to put on our official list of videos. So bear with us for like an hour or two, but you can find it. And if you guys want, we can give you a link.
yeah. Lazaro, is AlphaZero the chess thing? I've heard of AlphaZero. I haven't heard of MuleZero.
I'm pretty sure. Well, Lazar can unmute himself.
Yeah.
Yeah, AlphaZero is a nice.
Yeah.
Yeah, chess is nice, and chess is can be very complicated. But then if you compare it to something like Go, now that is amazing that there's models that can do that. It's, but yeah. So.
And I said AI cannot kill you. I made a mistake. It can kill you. It's used in.
It already has. No, actually, like Uber, I think it was Uber. Yeah, Uber had a testing situation wherein they were testing in one of their, California sites, and they had a self-driving car, and it was a cab, and it was horrible. It was the first, I think it was the first case of a self-driving car related death in the US, or at least cab.
Yeah, I mean that is definitely an issue when you're going with models, but overall, I think this is a good note to end on. But overall, if you compare the deaths by self-driving cars and cars driven by people, it's much less.
I mean,
yeah, there's going to be deaths, but
like considering how little prone to error they are, you're right. It's just like it made headlines a while back.
Yeah. Of course, yeah. Okay. So I guess we'll wrap it up here. Thank you guys for coming again. I said it many times, but I mean it. And please reach out to any of us if you have any more questions, anything. Yeah. Have a good one, guys. Bye.